Today we'll start looking at frequency response of some of these circuits. I think since, have you already looked at the basic frequency response of the common source, common drain and common gate? I assume you've already done all that. You have? Yes, no? Okay. Okay, so in that case what we'll do is quickly go through the common source, then maybe we'll do the some of the others, maybe common gate, no actually common drain, and then we'll do cascode. Okay, we'll look at the frequency response of all of these. Okay, so what we'll do is let's write out what this is going to look like. So first thing you can say is, since VBS is 0, neglect GMBS. Next we'll also neglect, for now we'll neglect the capacitance. Why? Because we're going to see what's going to happen directly from input to output. Since it appears directly across the input, we'll neglect it for now. But that, remember, that always assumes that you're driving with an ideal source. If your source had some impedance, if you had a VN and RN, then of course you would have to worry about the input capacitance also. So now we can write the transfer function for this. What will this turn out to be? What do you think it will have? Any zeros, any poles? Left half plane, right half plane? It has one pole. Where? Why? Across here it's going to have one pole. Okay. Anything else? CDB. We only neglected CGS and CGD. You are going to have CDB. You are going to have CGD. Okay. Anything else? CSB we can neglect because bulk and source are shorted. Okay, so what do you have? You have one pole and one zero, right? Okay. Now if you want to find out, so if I tell you to plot the, let's say the gain of this circuit as a function of frequency, what do you think it will look like? Is that some easy way to find out? Sorry? No. What I was asking is, without calculating out V out over Vn, if you want to find out what the gain of this is going to look like over frequency, what would you do? How would you look at it? How would you approach the problem? Poles and zeros. Okay, so that is one way to do it. So you can find out, how do you find out this is a little bit more complex, right? How do you find out the poles and zeros? The total capacitance at this node and the total impedance at this node, right? The conductance. Gi over Ci at any node is going to give you the pole frequency. Okay. What about the zero frequency? How do you find that out? See when the output goes to? What do you mean by output going to zero? The output voltage? V out. I know, I understand. So what you are saying is, when V out of S, magnitude of that goes to zero, right? You think it's ever going to go to zero here? Do you mean 0 dB or 0, which is minus infinity? Minus infinity or 0? Magnitude, not the dB, not in dBs, right? Magnitude goes to 0. Do you think V out is ever going to go to 0 here as a function of frequency? Why or why not? Okay, there is one pass from the input to the output. So what? there's one path here and there's a second path here, right? I assumed you meant one capacitive path, right? Or there are two paths, right? Okay. So if you want to find out, so what do you think the gain of this is going to be at very high frequencies? It's actually very easy. You don't have to calculate anything. Are you going to short the capacitors? You have to tell me. Is that correct? First of all, what is VGS at very high frequencies? If I plot VGS as a function of frequency, I am applying an input source, right? Okay. Obviously, okay. So assume, okay, now you need to start assuming, if you are going to start considering CGS, you need to assume there is some source impedance. So let's do that also. So I'm going to move this a little bit down. Let's call this VS and RS. Okay. What is VGS at very high frequencies? 0. Right? We are going to short the capacitor. So what is the signal current going through the transistor? Obviously 0. Gm times VGS. So signal current going through the transistor is 0. So as far as the signal goes, you can completely neglect the transistor. There is no signal going through the transistor. What about the other path? Are you going to short the capacitors? The capacitor divider, right? So in other words, you can short the capacitance when there are no other capacitive paths. If you have other capacitive paths to that point, you can't arbitrarily short it. Okay? Just remember that. Okay, so in this case, you just find out the voltage, very easy. So at very high voltages, so the reason I'm telling you this is, it's a good way to check your solution, right? If you're going to find out something V out over Vs, you find out a pole and zero, you find out the magnitude. This is a good way to find out, because you can try to look at the circuit, try to find out what happens at very high frequencies, and you already know what happens at very low frequencies, right? You already know the gain of the circuit, right? It's Gm over GDS. You already know that. Okay, so in most cases you would prefer to, what we'll try is when we write the transfer function of the overall circuit. Now this is a very simple circuit, so I'll just give you the solution, okay? But it is very useful to write it as the low frequency gain times some function of, right, polynomial function of S, right? You're going to have a numerator and a denominator, right? In this case, what do you have here for the poles? Okay, you're going to have, for the pole, you're going to have CDB, CL and CGD, right? Now for, let's neglect RS for now, okay? Makes it easier. So you have those capacitances over Gm, correct? That is the pole frequency. Oh, sorry. No, I made a mistake in my notes also. Okay, GDS, correct. Okay. Okay. If you calculate the zero frequency, turns out to be 1 minus SCGD over GM. Okay. Yes. We are going to see. Let's start looking at. So we are going to take this as a model and see how you write it out, right? Let's find out what omega z and omega p are. Then we'll see if there is some general method to write it out. Okay. This happens to be a right half plane 0. Okay, This happens to be a left half plane pole. Okay. So now, of course, you already know how to write the poles. So it is just the impedance, right? The conductance Gi. So if you want to write the pole, okay, at any node I, Ci is the total capacitance at node I, Gi is the conductance at node I. So that's pretty straightforward. How do you write an RHP0? Okay, in this case, if you had to draw a simple model, okay, you can show that if you have a transconductor with a capacitance C across it from input to output, you are going to have a right half plane 0. Okay. This is true in general. Okay. So you basically have an input output path which is the capacitance, and if that effective transconductance is Gm, in this case it's negative minus Gm, you get a right half plane 0. What happens if this is plus Gm? You get a left half plane 0. Okay. Okay, just remember that, remember the signs. Now if you had to plot this, so you have something at GM over GDS. In this case what I am going to do is, I am going to say it's 20 log, because now I want to plot in dB scale. At omega p starts to go down, well and good, you already know all this. And at omega z it goes back. So that at high frequency you already know what the gain is going to be, right? That's because of the capacitive divider. And you can also draw the phase. In this case, assume that I'm just drawing the excess phase. Okay. So in other words, you already have a minus which gives you 180 degrees. But let's assume I'm drawing the excess phase, so I'm going to start from 0. So what does this look like? When does it start going down? At omega p by 10. Okay. Till approximately 10 omega p. Okay. Here it's minus 45 degrees at omega p. Right? This is minus 90 degrees. Okay. Correct? Yes. No, because one of them is a left half plane pole and a right half plane 0, right? Because of that, if you had a if you had a left half plane 0, then it would go up. Okay. and this is the excess phase. Let me make that sure. Okay, so now it's pretty straightforward. So let's try doing the same thing for us. So this is for a common source, so fairly straightforward. Okay, then let's do it again for, okay, so first of all, before we go to the next circuit, suppose you had an input resistance. Now you will get a second, you will get another pole here. Okay, what is the frequency of that pole? GM into CGD into 1 plus. So of course you have a Miller effect here, right? 1 plus the gain. What is the gain? GM over GDS, right? So you'll have CGD times that, and then RI 1 over RS times the capacitance, right? So if you have enough gain in this, Miller effect could make sure that this pole is also pretty prominent. Okay, just remember that, because when we come back to the cascode, we are going to look at this effect again. Okay. Okay, so what are you going to do about this? What is this going to look like? So now that you have done the common source, let's do the source follower at least qualitatively. What do you think it's going to look like? What is the low frequency gain? No, it's not 1, right? It's GM over GMBS plus GDS plus GM. So it's less than 1. Okay, what is the high frequency gain? So now again you have a capacitive divider here, right? Right? Through CGS, now you have a capacitive divider. So again, it's not going to fall indefinitely. Okay, well and good. Now, what is the pole frequency going to be at? So now, assume that again this is driven by an ideal source. Okay? How many poles do you have? How many zeros do you have? What do you think their values are going to be? Input resistance is 0. So assume it's driven by an ideal voltage source. You only have one pole at the output, right? What is the pole frequency? GM by, why is it GM? Because the input impedance looking here is GM over CL plus CGS. Anything else? You are going to have a source to bulk capacitance. So you are going to have CL plus CGS plus CSB. Correct? Okay. How about the 0? So by the way, yes. No, we are going to write it out next. But I want you to do it qualitatively, looking at it without writing the equations. That is the whole idea, right? Because we already did it for the common source. So that's why I am asking you. What is the impedance looking here? So okay, so why don't you tell me, what is the impedance here at this point? That is the conductance, right? Okay, so GM plus GMBS. Okay, what is the total capacitance at that node? CGS plus C source to bulk plus CL. That is the total capacitance at that node. And we already decided that the pole frequency is going to be GI over CI, right? So it's just going to be, you can say, approximately correct? You can write this. Now is this going to be a left half plane 0 or a right left half plane pole or a right half plane pole? Left half plane pole. So you have a minus GM over CL plus CGS plus CSB. Well, typically if you have conductances and capacitances at nodes, they will almost always be left half plane poles. Okay? Sorry? Well, yes, that is true. That is absolutely correct. In this case, there is no clear, well, there is no clear method. It doesn't seem clear to us that the output is going to get unstable. That's true. That is true. There are cases where this circuit by itself doesn't become unstable, but there are cases if you modify the circuit a little bit, you can make it close to unstable. It may look unstable, may not be unstable, but may look unstable from a transient point of view. Okay? We'll just look at that next. Okay? What is omega z going to be? So let's make this more accurate. Right? We know that the output impedance is GM plus GMBR plus GDS. So let's put that also in there. Let's not leave it at just GM. Right? Remember, we found out the output impedance of a source follower is actually you have GM, GMBS and GDS. So let's make it more accurate. Okay? What is omega 0? Yes? You are saying it's minus GM over CGS. How did you come about this number, this value? The transconductance is GM, CGS between input and output. How did you arrive on the minus sign? Because it's a plus GM, right? The gain from input to output is actually, this is a positive. In the common source, you had a negative gain from input to output. Here you actually have a positive gain. Right? Okay? If you compare these two numbers, omega p and omega z, okay, you can clearly see from the denominator, numerator is almost the same for both. Okay, maybe a 1.1 or something, right? One is going to be 1, other right? One is going to be GM, other is 1.1 GM, maybe 1.2 GM. Okay, that's fine. If you look at the denominator, you have CL, which is definitely going to be significant, comparable to CGS for sure, right? So definitely omega z is going to be larger than omega p. So if you draw it on the S plane, omega p is going to be at one point, omega z is going to be larger to the left of that. Okay? So now let's say we can do something interesting. So now you see that it has a very similar form and they are actually both, on the left side. So you can actually do something interesting. If you add a capacitance between input and output, an extra capacitance, what will happen? If I add a capacitance CF, what is going to happen? The zero will move. You won't get a second zero. It will add to the capacitance, right? So the zero will move. What will happen to the pole? The pole will also move. Okay, well and good. Will they move by same amounts? Right? Zero will move actually much more because that has only CGS. In the other case it has CL plus CGS plus so on. So if you add enough CF, you can move these by different amounts, bring them right on top of each other. Right? So you have this and you have the pole and you can cancel the two. Okay? Okay, you add a CF across the gate source. how much CF do you need to add? You can easily calculate that. Why? Because you add some arbitrary CF, you can calculate the new pole and zero locations, equate the two, you find out what CF you need to add. So now let's find out how much CF you need to add. Okay? What is your new omega P? GM plus GMBS plus GDS minus of this, okay, over CGS plus CF plus CSB plus CL. Correct? What is your zero? Minus GM over, okay, CGS plus CF. Correct? So now what you're going to do is, you're going to set the two to be equal. Okay, so now you can cross multiply. Okay, what is easy is, you note that CGS and CF come together, right? So let's keep them together and that might be easier. So if you cross multiply here and here, right, when you on this side you are going to get GM times CGS plus CF. On this side you are going to get sum of all these three. When you bring one over to the other side, you just going, GM will get cancelled. You just have GMBS plus GDS. Okay. On the other side, all the others are going to have all the terms. Okay. So this is what you'll get. GM over GDS plus GMBS times CSB plus CL minus CGS. Right? Is that clear to everyone? Okay. So if you add a capacitance of this value, you can show that your pole and zero will exactly cancel each other out. Why do we want to cancel out the pole and zero? Maximum phase margin. Exactly. Right? Once you have one pole and one zero in the system, once you move them and cancel them out, you'll get a full broadband response. Right? You don't have a frequency dependence at all. Right? That's the biggest advantage. Okay? So what you would have had earlier is, let me do a better job with this. With the earlier one, what you had was, you started off somewhere close to 0 dB, which is 1. Correct? So you had one pole and one zero, right? The pole frequency was smaller than the zero frequency, so it starts going down and then flattens out again. Okay, what is the phase response going to look like? In this case, you are going to get something like this. You are going to get something like this, because now it won't go, because now the zero is a left half plane zero. Correct? So the phase will go back to 0. Now depending on the distance between omega p and omega z before adding Cs, this peak will shift, because now if this moves higher, then this will peak even more, or it will dip even more. Okay. Now once you add Cs, okay, once you add Cs, let's do one thing. You're going to get something like that, and your phase response is also going to look pretty good, right? Phase will not change, gain will not change. Okay, so that is the advantage of pole zero cancellation. So in other words, so if you had to draw it on the S plane, so you had your pole here, you had your zero here, so you basically moved both to the same point, okay, and you cancel them out. Well and good. There are two problems, okay. What do you think the size of CF is going to be? Why? How do you know it's going to be very high? Right? It's obviously related to GM over GMBS plus GDS. So we already know that GMBS is going to be at least maybe 1/10 of GM. So definitely CF is probably going to be somewhere like 10 times of CL. Okay? Which is very large. Okay? Okay? So that is one potential problem. What is the other problem? So if you see, there are other terms in your CF expression, CSB and CGS and so on, and GMBS and GDS. Now these are all functions of the bias point, as well as you may not know them accurately enough. If you are not careful, what you could do is, if your CF is not exactly equal to the number you want, in other words, what you will get is, if you end up getting something like this, where they don't cancel each other, but the pole and zero are right next to each other, okay, that's called a pole zero doublet. Okay, what will happen is, if you look at the transient response of such a system, okay, it will look really, really bad. Okay, it will take a long time to settle. Why? Because if you see, the closer they are, actually the worse it gets. Okay, because when you actually calculate out the transient response of the system, you will get a component which depends on the frequency difference between the two. The smaller it gets, the longer that component will take to settle. Okay, so that is a potential problem. Okay. Okay. So that is the source follower. Now let's just look at one more case. Suppose I did not have CL. Forget about the expressions we have drawn for a minute actually. So let's go to this point. Okay. Suppose I didn't have CL. What is the gain of this, the magnitude of the gain of this circuit going to look like with frequency? Qualitatively, what do you think? It should increase by in between you have capacitance, okay. Okay. The resistance is just GM. correct? The resistance at this point is 1 over Gm, looking up, that is the total conductance, correct? Okay, so yeah, so Gm plus GmbS plus GDS, 1 over that, okay? You're right, you're kind of right, so CGS is there, okay. CGS will? Exactly. In the earlier case when you had CL, you actually have a capacitive division effect. If you don't have CL, now you can say CGS is a short, right? Then your gain at high frequencies is actually 1. You can pretty surely say at low frequencies is actually less than 1. At high frequencies the gain is actually definitely equal to 1, right? So you actually see an increasing response. So if you actually plot the gain of this, it will do something like this. Okay? That is just an aside, but it's good to know because somebody brought up the idea of shorting the capacitors. I just thought I'll let you know about this. Okay? Yes, you're right, but typically what will happen is, okay, so it won't, if you have, so what are the relative values of CGS and CSB, right? CSB is typically much smaller than CGS. CGS is related to WLCox, whereas CSB is related to your junction capacitance of your diode. Typically that will be much smaller than the size. So you're right, that is a good point you brought up. In other words, it won't go all the way to 0. Okay? So it may go a little bit less than 0, but close enough. Okay? Yes? Anybody had a question? No? Okay. So let's take a cascode. I'm going to call this node X. What is V out over V in? Minus GM1 RD. So you know that. Okay. So which is the same as your common source amplifier. Okay. Now what can you tell about the poles of the system? How many poles do you have? Where are they going to be? Are you going to have any zeros? Okay. So if you have a, let us say, you're going to have that plus CGD2, right? You're going to have a CGD for signal VB is grounded. So you have CGD2 plus CDB2 plus CL is the total capacitance at the output node. What is the output impedance? Approximately RD. So you're definitely going to have a pole at 1 over RD times CL plus CGD plus CDB. Okay. So let's call this omega P2. Omega P1 is good enough. Right? Is that clear to everyone? Okay. What else do you have? You have a second pole in the system. What is that? At X. Okay. What is the value of that pole going to be? What is the impedance at that node? approximately 1 over gm, let's say, we'll neglect gmbs and so on, approximately 1 over gm. But now we are assuming, remember, we are assuming that RD is small compared to RDS2. Remember, always remember that, because you are going to see cases where RD is much larger actually. Okay? Okay, so it's approximately 1 over gm. What is the total capacitance at that node? So first of all, let's do this. So you have CGS2, CSB2, okay, then CDB1, you are going to add CDG1 also, okay, you are going to have those 4 capacitances. So for now I'll just call it CX, okay, it's easier, but you are going to have those 4 capacitances. What is the relative position of these 2 poles? Difficult to say because it depends on RD, but normally, right, RD would typically be larger than 1 over GM1. Okay? Sorry? Yeah. Okay? So typically omega P2 would be, yes. Node to ground. But when you evaluate the total capacitance, of course now you need to, you can set Vn to ground and then evaluate the overall capacitance, right? So sigma Ci, sigma Gi. Just like when you find out the conductance, you set your input signal to 0. You can do the same thing for your capacitance. Okay? No, because remember the same case as before, because you have Vn here. If you really had an input impedance for Vn, then you are right. You would have to be careful. It's not that simple. Okay? Now that we are assuming that Vn is, what are you going to do with Vn when you calculate the total capacitance at that node? Right? You have to short this. Right? When you short this, then CGS doesn't matter anymore. Okay? Okay, Gm over Cx. Okay? Now, one difference between this, okay, you have 2 poles, that's one difference. The other difference between this, what is the gain from Vn to, what is Vx over Vn? Gm1 by Gm2. Okay? Okay? Quite often this will be very, almost equal to 1. If you have equal size cascodes, they'll be equal. Okay? So let's say there's 1. Now what is the Miller capacitance at the input? It's just 2. Instead of, if you, let's say to compare with this, you built another normal common source with the same gain, let's say. Okay? Then you will have a very large Miller capacitance, because input to output capacitance, right, the output node would be directly at the drain of M1, so you would have a very large Miller capacitance. Correct? So that is one big difference. So you no longer have a very large Miller effect at the input. Now suppose RD was very large. Okay, so let me call this Zx. So you have Zx has 1 over Gm2, but the more accurate term is okay. If RDS2 is very large compared to RD, then you can neglect the second term. But suppose, I will give you a simple example. Suppose instead of a resistor you had a current source. Okay, now of course it's very large. Now Zx is very large. But suppose instead of a current source you had a cascode, right? Then RD would be like a GM-RDS squared kind of term. So definitely the second term is going to be significant. Right? In other words, the Miller effect is no longer just 2, it is going to be larger. But in a general case, for the cascode, the Miller effect will be less than what you can get for a normal common source. Okay? Yes. A cascade of two common sources. Okay? So let's say this has a gain of AV. Okay? So in this case it's minus AV. What is CN? In this case AV is going to be GM-RD. Correct? In the case of a cascode, what is it? 1 plus correct? So now it's obvious that this will in general, so what you're trying to do, you're trying to compare two amplifiers which have the same gain, let's say. You have to compare something, right? Or so this one will always be maybe 1 or 2 or something like that. Whereas this one, if you're trying to build an amplifier of a decent enough gain, it will be significant. Okay. Now should we go on? Yeah, let's go on. Okay, I'll just do maybe 2 more minutes. So let's say now, I think some of you might, people who have done the RF course may already remember this. Suppose now you're trying to cascade multiple stages, correct? And each one has some frequency response. Okay? In a typical, okay, so normally what do? We try to limit it such that you have a dominant pole case. So you have a single pole. Okay? So at the frequencies of interest, most systems can be approximated to be a single pole system. Because you know if you go to 2 pole, you have stability issues. Right? Okay? Suppose you have, let's say, let's take an amplifier with a pole at, let's say, 1 megahertz. You cascade 2 of these amplifiers together. What is the new 3 dB frequency going to be? Is it going to remain at 1 megahertz? Less? More? It's going to be less, right? Because you already have a 3 dB loss on the first one, you're going to have more loss on the second one, so it's definitely going to be lesser. Okay? So if you have n amplifiers, you can try to find out what the overall bandwidth is going to be for this cascade. Okay? Assuming that everything is a single pole system. Let me call this omega naught is the pole. Okay? I'm going to call this A naught. Okay? So we are going to approximate each one of them to be a single pole system. Okay. So what is the overall, let me call this, okay, yeah, H of S. What is the overall H of S? It's just going to be A naught over 1 plus S over omega naught whole power n. Correct? Okay? So now we want to, so now we know the transfer function. Now it's pretty straightforward to find out the 3 dB frequency. How do you find out? You find out the frequency at which, you know, your amplitude is 1 over root 2 times, right, the maximum value. Okay? So you're going to, what is the maximum value of this? A naught power n. Okay? So now I'm going to call it omega naught n. Okay. Whole power n. Okay. I'm just trying to find out the 3 dB frequency for the cascade, which is omega naught n. Okay. So of course a naught n gets cancelled, you can square and get the two terms, but what you get is okay. This is what you get if you simplify the other one. A naught gets cancelled, square, correct? So this tells you the amount of shrinkage you have in the bandwidth. When you cascade M equal amplifiers. Okay? And then now you can also replace it with the unity gain frequency. Unity gain frequency for the single pole system is nothing but A naught omega naught. Correct? So these two expressions are often useful to find out how much shrinkage you have in the bandwidth. Okay? So let's stop here and we'll continue on Tuesday.